It's the question that every person who's ever stood trackside has asked at least once. Why does a locomotive need so many wheels? A car has 4, a truck has 6, maybe 10 for the big ones, but a locomotive rolls on 8, 12, sometimes 16 or more wheels, and every single one is there for a reason that most people never think about. The answer isn't simple, and it isn't obvious, because the engineering behind locomotive wheel arrangements involves physics that took railroad engineers nearly 200 years to fully understand. The number of wheels on a locomotive tells you almost everything about what that machine was designed to do, how much it weighs, how fast it can go, and what compromises its designers made to balance competing demands that fight each other at every stage of the design process. This is the story of why locomotives have so many wheels, and why getting the number wrong has derailed trains, destroyed track, bankrupted railroads, and killed the careers of engineers who should have counted more carefully. The most fundamental reason locomotives have many wheels is weight distribution. A modern diesel-electric freight locomotive weighs approximately 420,000 pounds. That's 210 tons sitting on the rails. If you concentrated that weight on 4 wheels like a car, each wheel would carry over 100,000 pounds. The steel rail beneath it would deform like butter. The roadbed would collapse. The ties would shatter. The locomotive wouldn't move because it would be sinking into its own track. Spreading that same 420,000 pounds across 12 wheels means each wheel carries roughly 35,000 pounds, and each axle carries about 70,000 pounds. That's still enormous compared to highway vehicles, but it's within the load-bearing capacity of standard 136-pound rail on properly maintained roadbed. The concept is identical to snowshoes. A person sinks into deep snow because their weight concentrates on a small boot print. Snowshoes spread the same weight across a larger area, reducing the pressure per square inch below the level where snow compresses. Locomotive wheels do the same thing with rail and roadbed. More wheels mean more contact points, lower pressure per contact point, and less damage to the infrastructure the locomotive runs on. But weight distribution is only the beginning. The second critical reason for multiple wheels is traction. A locomotive can only pull a train if its driving wheels grip the rail firmly enough to convert engine power into forward motion. The maximum pulling force a locomotive can generate is determined by a simple equation: weight on driving wheels multiplied by the friction coefficient between steel and steel. That friction coefficient typically ranges from 0.25 in wet conditions to 0.35 in dry conditions. A locomotive with 420,000 pounds distributed across 6 axles has roughly 70,000 pounds per axle. With all 6 axles powered, that's 420,000 pounds available for traction. At a friction coefficient of 0.30, the locomotive can generate approximately 126,000 pounds of tractive effort before the wheels start to slip. Reduce the number of powered axles, and you reduce tractive effort proportionally. A 4-axle locomotive of the same weight puts more weight per axle, but has fewer axles generating pulling force. The total traction is lower because you've concentrated weight instead of distributing it. This is why the heaviest freight trains in the world are pulled by 6-axle locomotives. You need maximum weight spread across maximum powered axles to generate maximum tractive effort. 4-axle locomotives work well for lighter trains and switching, but they physically cannot generate the starting force needed to move 15,000-ton coal trains, or intermodal consists stretching 2 miles. The third reason is one that most people never consider: curve negotiation. A locomotive isn't just a weight sitting on rails. It's a weight that has to navigate curves, switches, and track irregularities, while maintaining contact with the rail and not derailing. Rigid wheelbases, the distance between the first and last axle in a non-pivoting group, determine how sharp a curve the locomotive can negotiate. A longer rigid wheelbase resists turning because the wheels at the front and back of the group want to travel in straight lines while the track curves beneath them. The wheels fight the curve by grinding against the railhead, generating enormous lateral forces that wear both the wheel flanges and the rail. Too long a rigid wheelbase, and the locomotive simply can't negotiate the curve at all. The wheels climb the rail and derail. This is why locomotives use trucks, also called bogies, which are separate wheeled assemblies that pivot beneath the locomotive frame. A 6-axle locomotive typically has 2 3-axle trucks. Each truck pivots independently, allowing the locomotive to negotiate curves that would be physically impossible for a rigid 6-axle arrangement. The truck transforms 6 axles from a rigid bar into a flexible system that follows the track's curvature. The pivot point allows the truck to swing through curves, while the locomotive frame above travels a smoother path. Without pivoting trucks, locomotives would be limited to nearly straight track, which doesn't exist in the real world. Steam locomotives made wheel arrangements into an art form because they had to balance competing demands that diesel locomotives largely eliminated. A steam locomotive needed driving wheels to provide traction, leading wheels to guide it into curves, and trailing wheels to support the firebox and cab. Each wheel type served a fundamentally different purpose, and getting the combination wrong produced locomotives that were dangerous, inefficient, or both. The White notation system classified steam locomotives by wheel arrangement. A 462, called a Pacific, had 4 leading wheels, 6 driving wheels, and 2 trailing wheels. The 4 leading wheels were mounted in a pivoting truck that guided the locomotive into curves. Without them, the first driving wheel would slam into the outer rail on every curve, generating forces that destroyed both rail and wheel. The 6 driving wheels provided traction. They were the only wheels connected to the engine cylinders, and their diameter determined the locomotive's speed characteristics. Larger driving wheels meant higher speeds, because each revolution covered more distance. But larger wheels also meant less tractive effort, because the mechanical advantage of the driving rod decreased. The 2 trailing wheels supported the weight of the firebox, which extended behind the last driving axle. Without trailing wheels, the firebox weight would have overloaded the rear driving axle, causing excessive wheel wear and track damage. Driving wheel diameter was one of the most consequential decisions in steam locomotive design, and it directly affected how many wheels a locomotive needed. Freight locomotives used small driving wheels, typically 57 to 63 inches in diameter. Small wheels provided high tractive effort through greater mechanical advantage. The piston's force was applied closer to the rail through a shorter moment arm, multiplying the pulling force. But small wheels limited top speed because each revolution covered less distance. To achieve any given speed, small wheels had to rotate faster, which stressed the reciprocating components, the pistons, connecting rods, and valve gear, to their limits. Passenger locomotives used large driving wheels, typically 73 to 80 inches in diameter. Large wheels covered more distance per revolution, achieving higher speeds at lower rotational speeds that were easier on the machinery. But large wheels reduced tractive effort because the longer moment arm reduced the force multiplication. A passenger locomotive with 80-inch drivers could cruise at 100 miles per hour, but couldn't start a heavy freight train because it simply didn't have the starting, tractive effort. This trade-off between speed and pulling power meant railroads needed different locomotives for different services, each with wheel arrangements optimized for their specific task. A universal locomotive that could do everything was a fantasy that the physics of wheel design wouldn't permit. The number of driving wheels determined how much weight a steam locomotive could put on the rail for traction. A locomotive with 4 driving wheels, 2 axles, could carry perhaps 80,000 to 100,000 pounds on its drivers. That was adequate for light trains on flat terrain. A locomotive with 8 driving wheels, 4 axles, could carry 200,000 to 280,000 pounds on drivers. That handled heavy freight on moderate grades. A locomotive with 12 driving wheels, 6 axles, could carry over 350,000 pounds on drivers, enough to haul the heaviest trains over the steepest mountain grades. Union Pacific's Big Boy had 16 driving wheels, 8 axles, carrying approximately 540,000 pounds. That massive driver weight generated the tractive effort needed to haul 3,600-ton trains over the Wasatch Mountains without helper locomotives. But more driving wheels created their own problems. Longer groups of driving wheels increased the rigid wheelbase, limiting curve negotiation. This is why articulated locomotives were invented. By splitting the driving wheels into 2 groups, each mounted in a separate frame that could pivot independently, engineers could put 12 or 16 driving wheels on a locomotive while maintaining the curve negotiation ability of a much shorter wheelbase. The mallet and simple articulated designs solved the curve problem, but they added mechanical complexity, weight, and maintenance requirements that partially offset the traction gains. Leading trucks served a purpose that seems obvious, but involved engineering that was anything but simple. A pivoting truck at the front of a locomotive acts as a pathfinder. As the locomotive enters a curve, the leading truck encounters the curvature first and swings toward the inside of the curve. This swing pulls the front of the locomotive frame toward the inside of the curve, reducing the lateral force that the first driving wheel exerts on the outer rail. Without a leading truck, the first driving wheel hits the outer rail with the full centrifugal force of the locomotive's mass. With a leading truck, that force is partially absorbed by the truck's pivoting action. The size of the leading truck mattered enormously. A 2-wheel leading truck, a single axle, provided basic guidance adequate for slow-speed freight service. A 4-wheel leading truck, a 2-axle bogie, provided far superior guidance at high speeds because the longer wheelbase of the truck created stronger centering forces and smoother tracking into curves. This is why passenger locomotives almost universally used 4-wheel leading trucks. The higher speeds of passenger service demanded better guidance than a 2-wheel truck could provide. Freight locomotives could get away with 2-wheel trucks because they operated at lower speeds where the guidance demands were less severe. Some designs used no leading truck at all, like the 060 switcher, because yard speeds were so low that no guidance beyond the driving wheels themselves was needed. Trailing trucks evolved from a simple afterthought into a critical design element as steam locomotives grew larger. Early steam locomotives had small fireboxes that fit between the driving wheels. No trailing wheels were needed because the firebox weight was carried by the drivers. As trains got heavier and faster, locomotives needed larger fireboxes to produce more steam. Eventually, fireboxes grew so large that they couldn't fit between the driving wheels and had to extend behind them. This overhang required support. The trailing truck was born. A 2-wheel trailing truck supported a moderate firebox extension. A 4-wheel trailing truck supported the massive, wide fireboxes that the most powerful locomotives required. The 4-wheel trailing truck wasn't just about weight support. It also improved ride quality at speed by providing a suspension point at the extreme rear of the locomotive. Without it, the rear of the locomotive would bounce and sway because the last driving axle's springs were optimized for traction, not ride comfort. The trailing truck's springs could be tuned specifically for ride quality without affecting traction characteristics. Some of the most successful steam designs used large trailing trucks specifically because they improved crew comfort during the long hours of high-speed running that passenger service demanded. Tender wheels added even more to the total wheel count, and they served a purpose that most observers overlooked. A large tender carried 25,000 gallons of water and 25 tons of coal. The loaded weight could exceed 400,000 pounds. Distributing that weight required as many wheels as the locomotive itself. A Fanage typical 12-wheel tender used 2 6-wheel trucks, each truck containing 3 axles. The 6-wheel truck was preferred over 4-wheel designs because it reduced the weight per axle to levels that standard track could handle. Some of the largest tenders used 14 or 16 wheels. The Centennial-type tenders built for Union Pacific's big boys rode on 2 4-axle trucks, 16 wheels carrying nearly 450,000 pounds of water, coal, and tender structure. Tender trucks also needed to negotiate curves, so they used the same pivoting bogie design as the locomotive's leading and trailing trucks. The coupling between locomotive and tender was a critical engineering detail. It had to be flexible enough to allow the tender to follow the locomotive through curves, strong enough to transmit pulling force when the locomotive was in reverse, and tight enough to prevent the two from separating during normal operation. Getting this coupling wrong could derail the tender on curves or separate the locomotive from its fuel and water supply at the worst possible moment. Diesel-electric locomotives simplified wheel arrangements dramatically, but the underlying physics didn't change. A modern 6-axle diesel freight locomotive, like an EMD SD70ACE, rides on 2 3-axle trucks, 12 wheels total. Every axle is powered by a traction motor. There are no leading wheels, no trailing wheels, no unpowered axles. Every wheel contributes to both weight distribution and traction simultaneously. This is one of diesel's fundamental advantages over steam. On a steam locomotive, only the driving wheels produced tractive effort. Leading and trailing wheels were dead weight from a traction perspective. They were necessary for guidance and support, but contributed nothing to pulling force. A 484 steam locomotive might weigh 450,000 pounds total, but only 275,000 pounds was on the driving wheels available for traction. A diesel locomotive weighing 420,000 pounds puts all 420,000 on powered axles. Every pound of locomotive weight contributes to traction. This efficiency of weight utilization means a diesel locomotive can generate more tractive effort per ton of locomotive weight than a steam locomotive. It doesn't need as many wheels in total because it doesn't waste any wheels on unpowered guidance and support functions. 4-axle versus 6-axle is the fundamental choice in modern diesel locomotive design, and it determines almost everything about what the locomotive can do. A 4-axle locomotive, 8 wheels, typically weighs 260,000 to 300,000 pounds. At roughly 70,000 pounds per axle, it stays within standard axle load limits. With all 4 axles powered, it generates approximately 75,000 to 90,000 pounds of starting tractive effort. That's sufficient for lighter freight trains, passenger service, and yard switching. A 6-axle locomotive, 12 wheels, weighs 380,000 to 420,000 pounds. At 65,000 to 70,000 pounds per axle, it also stays within standard limits, but generates 110,000 to 180,000 pounds of starting tractive effort. That's what you need for unit coal trains, heavy intermodal consists, and mountain-grade operations. The choice between 4 and 6 axles isn't about speed or horsepower. Both configurations can achieve the same top speed and carry similar output prime movers. The choice is about traction. 6-axle locomotives pull harder because they put more weight on more powered wheels. 4-axle locomotives are lighter, shorter, and more nimble in yards and on branch lines where the extra traction isn't needed and the extra length is a liability. Modern traction control technology has changed the wheel equation in ways that would have seemed like science fiction to steam-era engineers. Microprocessor-controlled wheel slip detection systems monitor each axle independently, measuring rotational speed thousands of times per second. When one axle begins to slip, the system reduces power to that specific traction motor within milliseconds, faster than any human could detect the slip. This means modern locomotives extract more tractive effort from each axle than older designs because they operate closer to the adhesion limit without crossing it. Older locomotives needed extra axles, partly because crude wheel slip control wasted adhesion. If one axle slipped, power reduction affected all axles simultaneously, reducing total tractive effort dramatically. Modern individual axle control means fewer axles can produce the same total tractive effort as more axles with older technology. This is one reason why modern 4-axle locomotives have displaced 6-axle units in some services. Advanced traction control wrings so much performance from 4 axles that 6 axles aren't always necessary for moderate tonnage trains. But physics still sets hard limits. No amount of electronic sophistication can make a 280,000-pound locomotive generate the tractive effort of a 420,000-pound locomotive. Weight on rail, still, determines maximum adhesion, and more axles still means more total weight within axle load limits. Electric locomotives add another dimension to the wheel discussion, because electric traction motors can be made smaller and lighter than diesel-electric systems, allowing different weight distribution strategies. High-speed electric trains, like the French TGV or Japanese Shinkansen, use powered axles throughout the train set, distributing traction across dozens of wheels rather than concentrating it in a locomotive. A Shinkansen N 700 series train has 56 powered axles across its 16-car formation. Each axle generates modest tractive effort, but the combined force of 56 axles is enormous. Distributing power this way reduces the weight per axle to levels that allow very high speeds without destroying the track. Concentrating the same total power in a single locomotive would create axle loads incompatible with high-speed running. This is why dedicated high-speed trains use distributed power, while conventional freight trains use concentrated power. Freight doesn't care about speed-induced track forces because freight trains run at 50 to 70 miles per hour. What freight cares about is maximum tractive effort, which means maximum weight on minimum wheels, concentrated in a locomotive that pulls hard at low speed. Passenger service cares about speed, which means minimum weight per wheel, distributed across maximum wheels, spread throughout a lightweight train set. The relationship between wheel diameter and speed persists in the modern era, though it's less dramatic than in steam days. Modern locomotive wheels are typically 40 to 42 inches in diameter. That's a compromise between traction and speed. Smaller wheels would provide more tractive effort through better mechanical advantage at the traction motor, but they'd rotate faster at any given speed, accelerating wear on bearings, flanges, and tread surfaces. Larger wheels would reduce wear rates, but increase the gearing ratio needed between traction motor and axle, adding weight and complexity. The 40 to 42-inch standard represents decades of optimization that balances competing demands for the typical mix of speeds and loads that freight locomotives encounter. High-speed passenger equipment uses larger wheels, typically 36 inches on bogies in train set configurations, because the design optimization prioritizes ride quality and reduced rotational stress at high speed over raw tractive effort. Wheel diameter also affects suspension design. Larger wheels raise the center of gravity, requiring stiffer springs to prevent excessive body roll. Smaller wheels lower the center of gravity but reduce the space available for suspension components beneath the car body. Every wheel dimension involves trade-offs that cascade through the entire vehicle design. Wheel wear determines how long a locomotive can operate between maintenance interventions, and the number of wheels directly affects wear rates and patterns. A locomotive wheel doesn't wear evenly. The flange wears faster than the tread, because flange contact with the rail involves sliding friction rather than rolling friction. On curved track, the outer wheel's flange bears against the railhead, scrubbing material off both surfaces. The wear rate depends on curvature, speed, axle load, lubrication, and the metallurgy of both wheel and rail. A locomotive operating in flat territory with gentle curves might run 200,000 miles between wheel turnings. The same locomotive assigned to mountainous territory with sharp curves might need wheel attention every 60,000 miles. Spreading wear across more wheels extends the interval between maintenance. A 6-axle locomotive distributes the total wear budget across 12 wheels instead of 8. Each wheel absorbs less total wear per mile, extending the service interval by roughly 30 to 40%, compared to a 4-axle unit in identical service. This maintenance advantage partly offsets the higher purchase cost of 6-axle locomotives. Over a 30-year service life, wheel maintenance costs are a significant fraction of total ownership expense. Derailment physics explains perhaps the most critical reason for getting the wheel count right. A train derails when lateral forces exceed the vertical forces holding the wheel on the rail. The ratio of lateral to vertical force, called the L/V ratio, must stay below approximately 0.8 to prevent wheel climb derailment. Vertical force comes from the vehicle's weight on each wheel. Lateral force comes from curving, wind, track irregularities, and dynamic effects. More wheels mean more vertical force distributed across more contact points, providing a larger safety margin against derailment. A lightweight 2-axle vehicle with high center of gravity is inherently more derailment-prone than a heavy 6-axle locomotive, because the L/V ratio reaches dangerous levels at lower lateral forces. This is why empty freight cars derail more frequently than loaded ones. The vertical force decreases when the car is empty, but lateral forces from curves and track imperfections remain the same. The L/V ratio increases and derailment becomes more likely. Locomotive designers calculate L/V ratios for every wheel position under every anticipated operating condition, including the worst-case combinations of curve radius, speed, wind load, and track irregularity. The wheel arrangement must keep every wheel's L/V ratio below safe limits across the entire operating envelope. Adding wheels provides additional vertical force that suppresses L/V ratios, creating safety margins that save lives. Some of the most spectacular wheel arrangement failures in history illustrate what happens when designers get the count wrong. Pennsylvania Railroad's duplex drive locomotives, the T1 and Q2, split their driving wheels into 2 separate groups, powered by independent sets of cylinders. The concept promised smoother power delivery, because each group of drivers could be smaller and lighter, reducing the reciprocating forces that caused rough riding at high speeds. The reality was catastrophic wheel slip, because each group carried only half the locomotive's weight for traction. When one group slipped, it accelerated suddenly, jerking the locomotive and sometimes triggering slip in the other group. The result was a violent bucking motion that passengers described as dancing on the rails. The fundamental error was dividing the weight among too many independent wheel groups. If all the driving wheels had been mechanically connected through coupling rods, as in conventional designs, the full weight of the locomotive would have resisted slip on every wheel simultaneously. The duplex arrangement turned a well-understood adhesion problem into an unsolvable instability problem by making the wheel groups fight each other instead of working together. The future of locomotive wheels is evolving in directions that would surprise most observers. Independently rotating wheels, where each wheel on an axle can rotate at a different speed, are being developed for high-speed applications. Conventional solid axles force both wheels to rotate at the same speed, which creates problems in curves where the outer wheel must travel a longer distance than the inner wheel. The speed difference is normally accommodated by the conical wheel profile, but at high speeds, this accommodation creates hunting oscillation, a lateral wobbling that limits speed and degrades ride quality. Independently rotating wheels eliminate hunting by allowing each wheel to find its own natural speed. The trade-off is loss of the self-centering effect that conical profiles provide. Active steering systems using sensors and actuators must replace the passive centering that solid axles provide for free. The technology is being tested on experimental high-speed trains in Europe and Asia. If successful, it could allow higher speeds with fewer wheels, because each wheel's stability envelope would be larger. But the added complexity of active steering introduces new failure modes that passive systems don't have. A solid axle with conical wheels has been centering itself on rails since 1830 with zero electronic components. Replacing that with sensors, computers, and actuators requires extraordinary confidence in the reliability of systems that don't have 200 years of proven service. Magnetic levitation eliminates wheels entirely, which sounds like the ultimate solution until you consider what wheels actually provide beyond rolling contact. Wheels provide braking force through friction. Wheels provide fail-safe support because gravity holds them on the rail even if all other systems fail. Wheels provide a speed reference because their rotation directly measures ground speed. Wheels provide electrical grounding through rail contact. Wheels provide fail-safe guidance through flange contact. Maglev systems must replicate every one of these functions through electromagnetic means, adding complexity and failure modes that wheeled systems simply don't have. A maglev vehicle that loses power must lower onto emergency skids because it has no wheels to coast on. A conventional train that loses power coasts safely on wheels that require zero energy to function. The wheel count is the final answer to an equation that balances weight, power, speed, curvature, safety, and economics. Getting the answer wrong costs money at best and lives at worst. The next time you count the wheels on a locomotive, you're not looking at engineering conservatism or industrial excess. You're looking at the precise number of steel circles required to solve a physics problem that involves 400,000 pounds of machine moving 20,000 tons of freight through curves designed a century ago on track maintained to tolerances measured in fractions of an inch. That's why locomotives have so many wheels, because physics demands every single one of them. Don't forget to subscribe so you don't miss future updates. Here's another video I've specially selected for you.